Okay, let's do the exercise problems in lesson 1. Reading exercise 1.1 now. So what is the force between two small charged spheres having charges of 2 into 10 power minus 7 Coulomb and 3 into 10 power minus 7 Coulomb placed 30 centimeter apart in air? Yeah, so it's a very simple problem. So exercise 1.1. So you have two charges. One is 2 into 10 power minus 7 Coulomb. There is a sphere, a small sphere, and there is also another small sphere here. Okay? So one has 2 into 10 power minus 7 Coulomb, and then the other one has 3 into 10 power minus 7 Coulomb. So this is, I call this as Q1, and this is Q2 is this. And they are separated, centers are separated by a distance of 30 centimeters. So 30 centimeters is equal to 0.3 meters. Okay. And they're asking you, so what is the force between the two small, this spheres basically, okay? So it's very easy, you can use Coulomb's law. So which is simply F is equal to K Q1 Q2 by R squared, right? Okay. But this is true only for point charges. But now you have spheres. But what have you seen last? For all the points which lie outside the sphere, you can treat the charges on the sphere to be concentrated at the center, right? So for all these charges, this will act as a point charge, and for all these charges, this will act as a point charge. So you can expect the application of the Coulomb's law straight away as a right approach. That will yield you the results actually. So you can simply use Coulomb's law. Because like you've got two small spheres, like separated by a fair distance, so you can treat these two as point charges. That's the main idea. So we can use it here. So what is this? This is going to be K is 9 into 10 power 9, we know that, and Q1 is 2 into 10 power minus 7, and Q2 is 3 into 10 power minus 7, and this is 30 centimeters or 0.3 meters. I can write this as 3 into 10 power minus 1, okay? So that is 0.3, right? The whole square. So what this will do is 3 squared and 10 power minus 2 is what you will get. Right? The 3 squared is 9, and 9 and 9 will cancel. So you get, maybe I'll do it again. 9 10 power 9 to 2 into 10 power minus 7 to 3 into 10 power minus 7, so divided by 9 into 10 power minus 2. So this 9 and this 9 will cancel, and this 10 power minus 2 and maybe will become 10 power minus 5. This is 7 minus 5, minus 7 plus minus 5 will become minus 12. We got 9 here. So effectively all these things, okay, will become 10 power minus 3. Okay, so I'm going to get 2 into 6 into 10 power minus 3, 10 power minus 3 newtons, or 6 millinewton force will be the force experienced by each sphere. This will experience 6 millinewton force, 6 into 10 power minus 3 newton force in this direction, and this is going to be experiencing 6 into 10 power minus 3 newton force in that direction. Okay. So both are positively charged, 2 and 3. So force of repulsion will take place. So it's a very simple problem to do, not much there. Second, 1.2. The electrostatic force on a small sphere of charge 0.4 microcoulomb due to another small sphere of charge minus 0.8 microcoulomb in air is 0.2 Newton. Then what's the distance between the two charges, two spheres? And second is, what is the force on the second sphere due to the first? So 1.2. So 1.2. So what have we got here? We got two spheres again. One is 0.4 microcoulomb, it's Q1, then Q2 is actually minus 0.8 microcoulomb, okay, and you don't know the distance between them. You don't know the distance between them. So they want you to find what have they given you? They said that force acting on it's like the force acting on wall, the 0.4 microcoulomb is 0.2 Newton. 0.2 Newton is the force acting on it. Okay. You can. So this is the problem. You can come to some conclusions straight away. First, this is a positive charge, this is a negative charge, so you must experience a force of attraction here, right? So the force of attraction must be here, and then the value of that force is 0.2 Newton. So 0.2 Newton force of attraction in this direction, okay? And clearly that will also get attracted to this with the same force. So this also will have this one. So 0.2 Newton in this direction. Okay. So you straight away answer the B part of the question. So what's the force acting on the other charge? It's 0.2 Newton towards the first charge. And what's the force experienced by the first charge? 0.2 Newton towards the second charge. Okay. So you can straight away answer the second question. Then what's the first part of the question? The first part of the question is, what's the distance of separation between them? That's easy again, right? So the force is given by the expression K, Q1, Q2 by R squared. So what you have is that gives you, what is the force? It's 0.2 Newton. It's 0.2, that is equal to 9 into 10 power 9. And what is the Q1? The magnitude of Q1 is 0.4 into 10 power minus 6, this is microcoulomb, and multiplied by, this is 0.8 into 10 power minus 6 coulomb. Okay? I can put a negative sign, but as I told you before, the negative sign just indicates that the force is merely attractive, so nothing else does it do. So the 0.2 is the magnitude. It's an attractive force. The negative sign will only tell you that this is attractive. Beyond that, the negative sign does not have any other significance. So I can just take the magnitude and do it like this. So divided by R squared, right? Okay. Now, so can I do this? And R squared is equal to, I can bring 0.2 this side, or I can do this, right? So 0.2, then 0.8 will be simply 4, right? 4 times 0.2 will give you 0.8. So I can do it like that. Okay, I can take this and then say 0.2 can do 2 also. I mean, I can cancel either this or that, it's up to you. I've chosen to cancel this 0.8. Okay, now R squared, now this is 1. So R squared is equal to 9 into 10 power 9, it becomes 1, right? 1, that is 4. And 10 power 9 into 0.4 into 10 power minus 6 into 4 into 10 power minus 6 by 1. 1 comes down. That's math. Okay? Okay, let's see. So what does this do? So this is minus 12 and this is 9. So 10 power minus 3 is what you get. Okay? Go here. then 10 power minus 3 into 10 power minus 3. So what have we got here? Basically 9 into 4 is going to be 36, right? 9 into 4, 36. 36 into 0.4. Okay? So what would that be? I can take that to be 36 into 4, 72 plus 72, 144 point, so 14.4. 14.4 into 10 power minus 3. Okay? So, it's 1.4 into 10, right? That's 14. So, if we do it properly, then it will be 1.44. Instead of doing it that way, what I'm going to do now is I'll do something else. 14.4, okay? I'll multiply this by 10 and divide it by 10 because r square I've got. I know the square root of 144 is 12, but I got only 14.4. So what I'm going to do now is I'm going to multiply this by 10 and divide this by 10. Okay? So the value will not change. But multiply 14.4 with 10, so that gives me 144 into, this is 10 power minus 3, this is 10 power minus, this is like 10 power minus 1. So you're going to have 10 power minus 4. Right? Okay. Wonderful. So this is what you get now. So that is your r square in meter square. Okay? So what is r? R is simply square root of this. Square root of 144 is 12. Square root of 10 power minus 4 is 10 power minus 2 meter. So that is actually equal to 12 centimeters. So these two charges are separated by a distance of 12 centimeters. So that's how you know this problem. It's a very simple problem, and we will discuss the second part of the problem. Okay. And so 1.3. Check that the ratio Ke squared by G Me MP is dimensionless. Look up a table of physical constants and determine the value of this ratio. Okay, what does the ratio signify? Okay. So what is this ratio given? Ke squared divided by G Me MP. Well, this has to be dimensionless. We've already done that. Think about it. Ke squared by r squared, that is electrostatic force between electron and proton. And then G MP by r squared, that's a gravitational force. So r squared and r squared cancel. So you're left with this Ke squared to G MP. Okay, so it's basically the ratio of two forces. So it has to be this has to be a dimensionless quantity. So this is a dimensionless quantity because it is equal to electrostatic force of attraction between electron and proton, so divided by gravitational force of attraction between the same. So this is in newtons and this is in newtons, so that gives you a dimensionless number. That's it. Okay. So I can write this as this, right? So it's actually Ke squared by r squared by G Me MP by r squared cancels. Then you get this point. Yeah. It's dimensionless. So that's one way of doing it. But the other way of doing it is take the unit of this K and then take the unit of this E squared and all that, and then G, ME, MP, take all these units and put them in the equation, and if you do that, then finally they all cancel each other out. Okay. Take the unit of K, take the unit of E, and then G, ME, MP, all the units you put in this expression, and you will find that they will cancel each other out very easily. Yeah. So that is another way of doing it. Actually, that's what I want you to do. So, but you can see that it's a dimensionless quantity. Next one, 1.4. Explain the meaning of the statement electric charge of a body is quantized. We have already discussed that because there is a basic unit, E, it's 1.602 into 10 power minus 19, and any other charge will have to be an integral multiple of this charge, whether it is positive or negative. So that's what we discussed in the class. So that's why we say that it is quantified. Because an atom is neutral, so by rubbing you remove electrons. So electrons have a specific charge, and so one becomes negative and the other one becomes net positive. But then it's net positive to that amount, 1.602 to the power minus 19. So you can only remove 1 electron, 2 electrons, 3 electrons, 4 electrons. You cannot remove 1.5 electrons from an atom. So the charge has to be quantized. So that's the meaning of that sentence. Next one. Why can one ignore quantization of electric charge when dealing with macroscopic, that is large scale charges? Yes, you can, right? Because we've talked about it. We talked about the wall, okay, and the glass, the whiteboard, and all these things. If you see, they're made of atoms, and then there is little spacing between them. But you can treat this to be continuous because there are so many of them that you treat it to be continuous. And the same principle applies to continuous charges too. Because when you have a large number of charges, the charges that you deal with in practical life, there's so much more than the electronic charge. So you ignore that the quantization effect of those charges. You treat those charges to be continuous. That's all. 1.5. When a glass rod is rubbed with a silk cloth, charges appear on both. A similar phenomenon is observed with many other pairs of bodies. Explain how this observation is consistent with the law of conservation of charge. We've discussed this again. An atom is neutral, you rub it, you remove an electron, and then this becomes positively charged. You do not put any charge there, you just remove the charge. And this charge, moves on to the other material. So basically, there is this conservation which is taken. You're not creating anything, but you have taken the charge from one place and put it on another material. So that's what it is. So the charge is conserved. Okay, then 1.6. 4-point charges. QA is equal to 2 microcoulomb, QB is equal to minus 5 microcoulomb, QZ is equal to 2 microcoulomb, and QD is equal to minus 5 microcoulomb are located at the corners of a square ABCD of side 10 centimeters. Then what's the force on a charge of 1 microcoulomb placed at the center of the square? Okay, so we'll do it. So I have a square. Okay, now this is A, this is B, and then this is C, and this is D. So what is the charge I have here at A? It's 2 microcoulomb. So 2 microcoulomb. And then what's the charge I have at B? That is minus 5 microcoulomb. And the charge C is 2 microcoulomb. And what's the charge at D? It's minus 5 microcoulomb. And what I'm going to do, I'm going to keep a charge of 1 microcoulomb at the center of the square. So which is the center of the square? I'm going to keep a charge Q of 1 microcoulomb. Then the question is, what is the force acting on the charge? Well, think about it. 2 microcoulomb. What will this do? This is positive, this is also positive, it will push it in this direction. Okay? And what will this do? this also will push it in this direction. So they will cancel each other out. This will push in this direction, this will push in this direction, and they are at the same distance from each other. Okay? So this value and this value, magnitude would be the same, but they act in opposite directions, and these two would be cancelled. But what about this? Well, it's 1 microcoulomb positive, this is minus 5 microcoulomb, so what will this do? This is going to pull it in this direction. And this is minus 5 microcoulomb, this is positive, this is negative, so this will also pull it in this direction. Okay? So these two forces will cancel each other. So this is F Q A, and this is F on Q due to C, and this is F on Q due to B, and this is F on Q due to D. Okay? So what happens in this case is there are forces acting, but then they will cancel each other out. So you can see that clearly, because you know F QA, vector F QA is equal to the negative of F QC vector, and F QB vector is equal to the negative of F QD vector. And what are the forces acting on this charge? So the total force F is equal to F QA vector plus F QB vector plus F QC vector and F QD vector. That's what happens here. F QA is actually minus F QC vector. F QB is actually minus F QD vector, and then plus F QC plus F QD. You see, this and this will cancel, and this will cancel. So effectively, there won't be any net force acting on this one. So okay, this is question number 6. So there is no net force acting on the charge that we're going to keep it at the center of this. Okay, hope this is clear to you. We'll continue. So 1.7. An electrostatic field line is a continuous curve. That's a field line cannot have sudden breaks. So why not? Because we know that when you have an electrostatic line, a field line, then that means it is just telling you in which direction a unit positive test charge will move if you keep it there. So that's it. So like that's what it means basically. So it's actually the electric field line is continuous in charge-free regions. So I have a charge here, and if we take this point, if we take this region, I'll have lines there. But if there is a charge at that particular point, then it will be discontinuous. Otherwise, electric field lines are continuous in charge-free regions actually. Okay. So we discussed that in the class. So that's the answer to that. It cannot have sudden breaks. Like if it has, they have to have sudden breaks, and there must be another charge there. Okay. So you have positive, negative, then the line goes from positive to negative, then there is a break at the places where you have charges. But if there is no charge, then it will be a continuous line. Second, explain why two field lines never cross each other at any point. We discussed this again in the class. We take a point, and we take suppose there is a charge, the field produced by a charge, and I bring another charge there. That charge will have a specific direction in which it will move. It cannot move in one of the two directions. So I cannot have lines crossing at any point. If you have a point, it will have only one direction. Because if I keep something at that point, it will move in one specific direction. So that is the reason why the electric field lines cannot cross each other. To give you the illusion that it can move either in that direction or this direction. No. The charge you keep there can move only in one direction. So they cannot cross each other. Discuss that again. Okay. 8. 2 point charges QA is equal to 3 microcoulomb and QB is equal to minus 3 microcoulomb are located 20 centimeter apart in vacuum. Then what's the electric field at the midpoint O of the line joining the two charges? And second, if the negative test charge of magnitude 1.5 10 to the power minus 9 Coulomb is placed at this point, what is the force experienced by the test charge? It's easy. First, 1.8. Two charges, QA and QB. QA values 3 microcoulomb and this is equal to minus 3 microcoulomb, and they are separated by a distance of 20 centimeters. Okay. Now the point is, what is electric field at the midpoint O of the line AB joining the two charges? So this is A, this is B. So this is the midpoint. We call it as O. What is the distance? It's going to be 10 centimeters, right? So this is going to be 10 centimeters here, it's going to be 10 centimeters there. To find the electric field, what I'm going to do, I'm going to bring a unit positive test charge. So unit positive test charge, so this charge is going to be repelled by QA. So that is E due to A, and this is again positive charge, but this is negative charge. So this is again going to be attracted by this charge, so that's EB. So the net field will be the sum of these two. So what is my EA? My EA is actually equal to K into QA by R square. So this is 9 into 10 power 9 into 3 into 10 power minus 6. So divided by this 10 centimeters, which is 0.1 meter, which is 10 power minus 1 meter, right? So 10 centimeters. So that is 10 power minus 1 square. Okay, it's 10 centimeters. So if I do this, then what will I get? This is 10 power minus 2. So this will become 10 power minus 4 now. So 9 into this one 27 into 27 into 10 power 5 Newton per Coulomb. So that's the force in this direction. So what about EB? Same, right? It's K QB R square. Again, I can put negative sign here, but that only tells me it's an attractive force in that direction, that's all. Okay, so this also will have the same value. Effectively, I have 27 into 10 power 5 Newton per Coulomb. Okay, but what is the net E field? The net E is actually equal to EA plus EB, and both of them are in the same direction. So I can simply say it is EA plus EB, which will be 27 into 10 power 5 plus 27 into 10 power 5 Newton per Coulomb. So that is 54 into 10 power 5 Newton per Coulomb, or it's equal to 5.4 into 10 power 6 Newton per Coulomb. So roughly 5.4 million Newton per Coulomb. So that is the strength of that field at the very center. So what's the next point? The next point is, the next part of the question is, if a negative charge, test charge of magnitude 1.5, 10 power minus 9 Coulomb is placed at this point, and what is the force experienced by the net charge, test charge? Fine. Okay. So you are going to place a test charge here. But that is 1.5 into 10 power minus 9 Coulomb. And what's the force experienced by it? So the force experienced by the charge is actually simply Q to E. Right? So Q into E. So what's Q here? Q is 1.5 into 10 power minus 9 microcoulomb. And what is E value here? That is 5.4 into 10 power 6 per coulomb. But you see, Q is a negative charge, so it won't move in the direction E. So this will be the direction of E, right? So this will be the direction of E. That is E. Sum of EA plus EB. But if we keep, that is, this direction is for positive charges. If we keep unit positive charge, it will move that way. But if we give a negative test charge, that will move in the direction, opposite direction of E, right? So because this will now attract that negative charge, this will repel that negative charge, so the charge will experience a force in this direction. So simply, this is E direction, but then you have Q, which will be in the, which is negative charge now. So the net force will be in this direction. Okay. So the force is going to be equal to 5.4 into 1.5. So that is another 2.7 added. So 8.1, right? So 8.1 minus 10 power 6 Newton per coulomb, meaning that this force is acting in the opposite direction. The direction opposite to the direction of E. That's what it is. Okay? So this E direction, you took this to be the E direction. I probably will say maybe this one and this one, this vector. Unit vector in the E direction. Okay. Opposite to the vector. I hope this is clear to you. So what about the next problem? The next problem is 1.9. A system has two charges, QA is equal to 2.5 into 10 power minus 7 coulomb and QB is equal to minus 2.5 into 10 power minus 7 coulomb, located at points A 0 minus 15 and B 0 plus 15 centimeters. They have given you the coordinates in 3 dimensions, x, y, z, respectively. And what are the total charge and electric dipole moment of the system? Okay, and that's easy. 1.9. Right? So let me take, I'm going to go for a 3-dimensional space. Now this is. So this is x, this is y, and this is z. Okay. Now let's see. First one is QA, which is kept at 0 minus 15 centimeters. Okay. So this is x is 0, y is 0, then z is minus 15. This is positive z direction. So the negative z direction must be here. This must be negative z, right? So minus 15 here. So that is QA. That's kept there. And what about the next one? QB is kept at 0 plus 15. So it is 0, x is 0, y is 0, this is plus 15. So this is QB. But QB is a negative charge which is kept on the positive z-axis, and QA is a positive charge kept on the negative z-axis. So what is this? So this is 15 centimeters from the origin, and this is 15 centimeters from the origin. Now, so what's the dipole moment? So the dipole moment is simply, so P vector is actually equal to 2AQ magnitude, and then in the direction of the dipole vector. Okay, so which is a positive charge? The positive charge is this. QA is positive and QB is negative. Right? So P direction is what? P will go from negative charge to positive charge. Right? So this is the direction of P. Okay? So it's the direction of P, which is actually the minus z direction. It's not the plus z direction. It will be in the minus z direction, right? So that is minus k direction. This is I, this is I, this is j direction, this is k direction. So that is minus k direction. Okay? So it's minus k direction. So what's the direction? It's minus k. That's the direction, we got the direction. That's in this direction. Then what's the magnitude of that, the dipole? So 2 into, what is this distance from the center? 15 centimeters. And the total is 30. Yeah, 30 centimeters. Or twice 15. So it is 15 into 10 power minus 2. What is Q? Q is minus 2.5 into 10 power minus 7. So 2.5 into 10 power minus 7. So that's it. So that gives you 30, or 2 into 2.5 is 5, 5 into 15 is 75, right? So 75 into 10 power minus 9, the minus k direction. So that gives you, I can convert this, right? I can make it as minus 7.5 into 10 power minus 8 k. Okay, that's my dipole moment. So dipole moment is simply one of the charges multiplied by the distance of separation between the two charges. So that is, distance of separation is 2a, and q is one of the magnitude of one of the charges, and the direction is from negative charge to the positive charge, and that is this. This is how you do this. So next one. Electric dipole moment 4 into 10 power minus 9 Coulomb is aligned at 30 degrees with the direction of a uniform electric field of magnitude 5 into 10 power 4 Newton per Coulomb. Then calculate the magnitude of the torque acting on the dipole. It's very simple. So 110. So there is a dipole kept in a uniform magnetic field. So it's very easy for you to calculate the torque. So what's the torque? So the torque on dipole is equal to P cross E. Okay? So what is P here? P is 4 into 10 power minus 9. Power minus 9. And it must have some vector. I will come to that. So this is, okay. Even before that, I will expand this. What is P? It's going to be P sine theta. This is some unit vector, perpendicular vector, right? Unit vector in the direction perpendicular to both P and D. That's a cross product. So I got 4 into 10 power minus 9 to minus 9. And what is the E value? Is 5 into 10 power 4 Newton per Coulomb. So 5 into 10 power 4 Newton per Coulomb. So that is my, this is my P, this is my E, and then I should have sine theta, the angle between them. So what's the angle between this? It's like this, right? So if you have a field like this E, and then your P is like this. Okay? The dipole is something like this. The dipole is like this. This is negative Q and this is positive Q. So the dipole is kept like that. So the angle between the dipole and E is 30 degrees. So sine 30 will be half. So sine 30. Okay? So that is going to give you 1 by 2. So I'm going to have this would be 1 by 2, right? Simply this 1 by 2. So this 2 and 4 will cancel 2. 2 into 5, 10. Now 10 power 5, 10 power minus 9. So that is going to give me, if I do that, if I do this, then I'm going to 10. 2 into 5, 10. 10 power 4, 10 power 5. 10 power minus 9. So 10 power minus 4 Newton meter. Okay, that's the magnitude. The direction, it will be perpendicular to both the vectors. They have not given you the direction of P and E, so you can ignore that. But you can conclude that the vector is going to be, the torque vector is going to be perpendicular to both this and that. That's all. Okay. So you have 90 degrees to this, and then 90 degrees to this. Something like that. Okay. Both the vectors can have. I hope this is clear to you. 110. Okay. Then 111. So 111 is basically easy. Okay, a polythene piece rubbed with wool is found to have a negative charge of 3 into 10 power minus 7 Coulomb. And estimate the number of electrons transferred from which to which. Okay, that's another question. Okay, from where to where. You know, like when wool is rubbed with polythene, then where the charges will, the electrons will move, right? So, and then what's the number? Is there a transfer of okay? What's the number of electrons? Okay, a number of electrons can be easily calculated, right? So what's the charge you got here? 111. The charge you got, the Q you have is 3 into 10 power minus 7. 3 into 10 power minus 7 Coulomb. So how many electrons? Okay. How many electrons will make this? So this is equal to, must be equal to n into E, right? So a certain number of electrons are, leaving, right? So will give you this one. So how many electrons left? So n into E. So you know that n into 1.602 into 10 power minus 90 is equal to 3 into 10 power minus 7. So n can be easily calculated 3 into 10 power minus 7 by 1.602 into 10 power minus 90. Okay, so you can easily say this 3 is 1.6 roughly 2, okay, then it's 10 power 12. So you can say that like 10, roughly 2 trillion electrons had to move from from the wool to from polythene to wool. Yeah, because polythene is found to be positive. So electrons must have left polythene to wool. Yeah, so leaving polythene positively charged. So that's the answer to that question 1.11. Another question as this like in 1.11 itself, is a transfer of mass from wool to polythene? No, most certainly not, because first of all, from the electrons move from polythene to wool. So there was no transfer of mass from wool to polythene. That didn't happen. Only electrons moved from polythene to wool. Even there, if you think about it, there's not much of a mass transfer because electronic mass is very, very, very small. And kind of ignore it. It's very small. Yes, there was a little bit of mass transfer from polythene to wool, not from wool to polythene. But it is from polythene to wool, electrons moved. But that mass transfer is negligible. You can ignore that basically. Okay? But most certainly, there was no mass transfer from wool to polythene because polythene became positive. So the electrons moved from polythene to wool. So that's the second part of it. Okay, then we'll move on to 1.12. Two insulated charged copper spheres A and B have their centers separated by a distance of 50 centimeters. Then what's the mutual force of electrostatic repulsion if the charge on each is 6.5 × 10⁻⁷ Coulomb? The radii of A and B are negligible compared to the distance of separation. It is very, it can be very easily done. So you're talking about two copper spheres and given you charges and the distance is also given, you should be able to calculate the force of repulsion on them. Okay. So you can treat them as point charges because they've said that the radii can also be ignored. Okay, so that's very easy to do. I'm not going to do it now. Then B. Then what's the force of repulsion if each sphere is charged double the above amount and the distance between them is apt? So we've done that already, I suppose. Okay. So now we're doubling the charge and then the distance is apt. Okay, so what will happen now? So 1.12. Very simply. So you have two charges, Q1, then Q2, and then there is this distance R between them, right? So we'll do it generally. So you don't have to worry about the calculation part with the numbers. So what's the force of attraction? As such, the force of attraction is equal to K to Q1, Q2 by R squared. Now what are you trying to do? You are trying to double the charge on each sphere. So now, if it is K1, now you have 2, if it's Q1, you have 2 Q1. If it was Q2 before, now you have 2 Q2. So 2 Q2 and you also double the distance. Okay? So it's 2 Q2, but now this is Q1, this is 2 Q2. The distance is actually 2R. Double the distance actually. Or rather, double or what? So the distance is apt. Okay, so it's like this. So the distance is kind of apt. So you move here. So 2 Q2. So 2 Q2. So this is R by 2. So what is going to happen now? So the new force, which is F dashed, is equal to K. This is 2 Q1 and then 2 Q2. So divided by R by 2 the whole square. So that should give you K Q1 Q2 by R squared into this 2 into 2 is 4 and this 2 squared will go up into 4. It's 16. So the new force is going to be equal to 16 times the old force. So whatever force you calculated for the first part, you need to multiply that with 16 to get the new force. That's all there is to it. Then 13. Suppose the spheres AB in exercise 1.12 have identical sizes. A third sphere of the same size but uncharged is brought in contact with the first, then brought in contact with the second, and finally removed from both. Then what's the new force of repulsion between A and B? Okay. So 1.13 is the extension of 1.12 where you have Q1, you have Q2, but Q1 is equal to Q, same, right? Q2 is also equal to Q, equal charges. Then you are bringing in this one's out. Now you are bringing in a third sphere of identical size, and you are touching this. Then what will happen? The charges will be shared equally because they are the identical sizes, right? So the charge will be shared equally. So when you bring the third sphere and then touch this sphere, then Q1 will now have Q by 2. Okay, first step. In the first touch, this is what happens. And Q3 is going to have Q by 2. Then the second touch, I am taking Q3 and touching this. Then what will happen? Then what's the total charge now? Q3 has Q by 2, second, right? Q3. So Q3 has Q by 2 and this has Q. So now the total charge is 3 by 2 Q, 1.5 Q. So 1.5 Q is the total charge. Now I'm bringing these two charges together. And 1.5 Q charge is going to be shared equally by these two. So each will have 0.75 Q, okay, or 3 by 4 Q, right? So at the second touch, Q2 will have 3 by 4 Q, because total is 1.5. Now going to be equally shared. So Q2 will have 3 by 4 Q and Q3 will have 3 by 4 Q, okay, of the second touch. But we are not bothered about Q3. So we did this touching business and removed Q3. Now you are left with Q1 and Q2. So now Q1 is Q by 2 and Q2 is 3 by 4 Q. Then what's the force between them? So that's easy to calculate, right? F is equal to K into, instead of Q1, you're going to have Q by 2, and instead of Q2, you're going to have 3Q by 4, so divided by same R squared. They didn't do anything to the distance. So that gives you 3 by 8 K Q squared R squared. Okay? Previously, initially what was the force? Before you did anything like this, what was the force? The original force, okay, was equal to K, Q and Q squared by R squared. That was original. Now this is new. F dash is now 3 by 8 K Q squared by R squared. So the new force is actually 3/8 of the old force. So now F dash is actually equal to 3/8 of old force. Okay, so this is how you do this problem. Hope this is clear to you.